Hello. Okay. Hello students. My name is Kavita Tiwari and we are going to learn about irrational numbers and then irrational numbers on a number line, decimal expansion of real numbers and then real numbers on a number line in today's class. So basically, firstly we need to know what are irrational numbers. Irrational numbers are the numbers which cannot be written in the form of p by q, where p and q are integers and q is not equals to 0. So it is just opposite of the rational numbers. Rational numbers were the numbers which were written in the form of p by q, where p and q are integers and q is not equals to 0. So let's take an example of a rational number. The rational numbers here are, let's say we have a rational number as 1 upon 2. So 1 and 2 both are integers, and we can also see here that q, that is 2, is not equals to 0. Similarly, the definition of irrational number is irrational numbers are the numbers which are not in the form of p by q, and p and q are integers and q is not equals to 0. Some of the examples of irrational numbers are root 2, root 15, pi, and we can say 0.101101110 and so on. So these types of numbers are the irrational numbers. Next, we are going to locate some irrational numbers on a number line. So before moving there, let's say we have a number which we can write in the, we have an irrational number. Let's say the irrational number is 1.02020202 and so on. And we need to write this number in the form of decimal. So what we are going to do in this case, we will consider, we can see that we can see that after the decimal point, the number is getting repeated again and again, right? 0.0202 and so on. For this, what we will do, we will first consider this part as x and then write the number as 1 plus x. Okay. Now, this number is actually equals to 1.020202 and so on. So again we will see, if we multiply this by 10, let's say we are going to multiply it by 10 times x. So this will become 10.202020 and so on. So it will be 10 plus x, which is again equals to x. Let's locate these irrational numbers on the number line. So let's take an example that we are going to locate root 2 on a number line. We know that root 2 is an irrational number. And how can we locate an irrational number on a number line? Basically, what we learn is that we locate just real numbers, we locate just integers or some kind of fractions on a number line, like we can locate 1, 2, 3, 4 and some kind of fractions like half, 1/4 or 1/3. So how can we locate these irrational number on a number line? So if we are going to locate root 2 on a number line, let's take a square which is of which side length is 1 unit. The side length of this square is 1 unit, and if we draw a diagonal in this square and then we partition it, then it will become a right angle triangle like this. This is a right angle triangle whose hypotenuse, whose perpendicular and base is of unit length. So by using Pythagoras theorem, we will be using the Pythagoras theorem, which says Pythagoras theorem says that square of your perpendicular plus square of the base is equals to square of hypotenuse. So hypotenuse will be equal to root of square of perpendicular plus square of base. So in this case, the hypotenuse will be equal to root of square of perpendicular. 1 square is 1 plus again square of base, 1 square is 1. So the hypotenuse is root 2. Now, how can we locate this root 2 on a number line, and what is the use of this? So basically, we know that root 2 is bigger than 1. So with the help of a compass, we will be locating this on a number line. We will start from 0, take a compass which is of length root 2, and then we will use this compass and measure on number line till where the root 2 is there, starting from 0, and then we will locate it on the number line. So basically if 1 is here and we will again draw a right angle triangle from here, our radius would be root 2, and we will take a compass and then draw a circle. The point where it cuts the number line will be the point where root 2 would be located. And similarly we can locate another numbers as well on the number line. Let's say we need to locate root 3 on the number line. So for that, let's have a number line first. Here is the number line. Let's start the number. Let's have the number line is starting from 1. Or the number line is starting from 1. We can consider the arrow point as 0. Now we are going to locate root 3 on the number line. For that, what we are going to do, we will consider a right angle triangle. Let's have a right angle triangle. This is a right angle triangle where, let's say, one of its length from, let's say its base is having length as root 2 and its perpendicular is of unit length. So again we will use the Pythagoras theorem. Which says that the hypotenuse is equals to root of square of perpendicular plus square of base. So here the hypotenuse is root of square of 1 is 1 and square of root 2 is 2. So hypotenuse is again root of 3, which is root 3. In this way we can locate any of the rational number on a number line. So here we are locating root 3. In the previous part we located root 2 on the number line. So in this case what we are going to do, we will see first the base is of let's say the perpendicular is of unit length. Let's draw a perpendicular which is of length root 2. So the hypotenuse would be of root 3 length, and let's take this root 3 as a radius, and using the compass we will draw a circle. The point where this circle cuts the number line would be the point which is root 3. So in this way we can locate any rational number on a number line. We can locate root n for any positive integer n, and after root n minus 1 has been located. Now let's have some example. You can state whether every irrational number is a real number or not with your justification. And also we will see the example. Every point on a number line is of the form root m, where m is a natural number and every real number is an irrational number. So these are the 3 points which we will be discussing in our next class. And let's continue for today's class. Now the decimal expansion of real numbers. Decimal expansion of real numbers, basically we are going to expand the decimals, and let's have some example. Let's have some numbers which are in the form of decimal. Let's say we are having a fraction which is 10 divided by 3 or 10 third. So when we divide 10 by 3, we will be getting 3.3333 and so on. It is 3 decimal. Let's have another decimal. When we divide 7 by 8, we will get 0.875. And let's have one more decimal as 1/7. And when we divide 1 by 7, we will get 0.142857. So basically, what are the differences in these decimals? The differences in these decimals is that the remainder, when we are dividing these numbers, in the first case the remainder would be 1, 1, 1, 1 and so on. When the divisor is 3. In the second case, the remainder get vanished. The remainder was first 6, then 4 and then 0. So the remainder got vanished after a certain point when where the divisor was 8. And in the third case, the remainder was 3, 2, 6, 4, 5, 1, 3, 2, 4, 6, 5, 1 and so on. So the remainder was again and again repeating. The divisor was 7. Okay. So have you noticed anything? You should have noticed at least 3 things. And those 3 things are the reminders either become 0 after a certain stage, just like you have seen in the second example, which was 7/8, where the remainder got vanished after in the third time. So the remainder either becomes 0 after a certain stage or start repeating themselves. Like in the case number 3, the remainder was repeating, and in the case number 1 also the remainder was repeating. The number of entries in the repeating string of remainder is less than the divisor. In 10 third, one number repeats itself and the divisor is 3. In the 1/7, there are 6 entries which were 3, 2, 6, 4, 5, 1. Let me highlight it for you. These are the entries which are repeating. Okay, let me underline the entries which are repeating. In the first one, 1 is repeating again and again. In the third one, the repeating numbers are 3, 2, 6, 4, 5, 1. Divisor was 7. So there are 6 entries, 3, 2, 6, 4, 5, 1 in the repeating strings of remainder, and 7 is the divisor. Now the third thing which you must have noticed is if the reminders repeat, then we get a repeating block of digits in the quotient. Just like in 10 third, 3 repeats in the quotient, and for 1/7 we get the repeating block 1, 4, 2, 8, 5, 7 in the quotient. This is the quotient. Okay. Now we have noticed this pattern using only the example of these three. So it is true for all rationals of the form p by q where q is not equals to 0. So on the division of p by q, two main things happen. Either the remainder becomes 0 or never becomes 0, and we get a repeating string of remainders. Let's take first case as the remainder becomes 0. When the remainder becomes 0 at a certain stage. So let's take the example of 7/8. What we found is that remainder is becoming 0 after some step, and the decimal expansion of 7/8 is 0.875. Other example of these type is, let's say, half, where the remainder becomes 0 after a certain stage, which is 0.5. Let's take another example, which is 639 divided by 250. In this case, if we divide these numbers, we will be getting 2.556 as a quotient, and the remainder will become 0 in the third step. Okay. So in all these cases, the decimal expansion terminates or ends after a finite number of steps, and we call the decimal expansion as numbers terminating. So this type of expansion is called as numbers terminating. Okay. Let's take case number 2, where remainder never becomes 0. In this case, let's take the example 10 third, where the answer was 3.3333 and so on. And another example is 7/8. Oh, okay, I'm sorry. Another example is 1/7, where the quotient is 0.12142,857. The quotient is actually the answer would be repeating, having a repeating string, and we will write these type of number as 0.142857 bar. Okay, where the bar above the digits indicate the block of digits that repeats. So these examples are giving us non-terminating recurring decimal expansion. These are repeating, so we will say these type of expansion as, let me write here for you. These are non-terminating recurring. Okay. Now suppose on the other hand, on your walk on the number line, you come across a number like 3.14268 whose decimal expansion is terminating, or a number like 1.272727 and so on, which is 1.27 bar, whose decimal expansion is non-terminating recurring. So can you conclude that it is a rational number? What do you say? Think about it and tell me in the next time. Okay. Now let's have some examples. Let's have an example. We need to show that 1.272727 can be expressed in the form of p by q, where p and q are integers and q is not equals to 0. So let me write here for you. We need to show 1.27 bar can be expressed in the form of p by q, where p and q are integers and q is not equals to 0. And how are we going to do this? We are going to work out on this. Just I have given an example in the very first slide. So similarly we are going to do this also. First we will consider 1.272727 so on as x. We will say this number is equal to x. Now since two digits are repeating, 2 and 7 are repeating again and again, so we will be multiplying this x by 100. So in the next step what we do, we will do 100 times x, which is equals to 127 0.272727 and so on. Now this 100x is equals to, actually it is equal to 126 plus 1.272727 and so on. Again this 1.272727 and so on, I mean 1.27 bar is the number which is equal to x, so we can write it as 100x is equal to 126 plus x. Okay, in the next step what we are going to do, we will solve and simplify it. So this would be equal to 99x equals to 126, and then we will find the value of x. So x will be equal to 126 divided by 99, which is equal to 14 divided by 11. Now it has been simplified, and 1.27 bar is equal to 14 upon 11, where 14 and 11 both are integers. The denominator, which is q, is equal to 11, which means it is not equals to 0. So we have written 1.27 bar in the form of p by q,